Welcome. Calculus is often treated like a cookbook, memorizing recipes without understanding the chemistry. But today, we're going to look at the fine print. We will explore why the phrase with respect to is the single most important concept in calculus. It is the hidden engine of the channel and the bridge that connects static algebra to the dynamic world of physics, motion, change, and life itself. Let's start with a deceptive question. Consider the standard formula for the area of a circle. A equals pi r squared. If I simply ask you, what is the derivative of A? Most of you will immediately answer 2 pi r. You instinctively apply the power rule, bring down the 2, and it feels correct. But this answer is incomplete. In fact, without context, it might be meaningless. Let's apply a reality check. Imagine an inflating spherical balloon. If I ask for the derivative of area, I am asking about the rate of change, but a rate relative to what? I could be asking, how much does the area grow for every inch of radius we add? That's a question about geometry. The universe is the circle itself. But I could also be asking, how fast does the area grow per second as we pump air in? That's a question about physics. The universe is time. This is the trap. Your answer 2 pi r describes the geometry. It cannot possibly describe the physics because the formula A equals pi r squared knows nothing about the air pump. It doesn't know if we are inflating it slowly or quickly. To answer the physics question, we need more information. This brings us to the definition. A derivative is fundamentally a ratio, a small change in output divided by a small change in input. The denominator is the with respect to. If you ignore the denominator, you don't know which universe you're in. This is why Leibniz notation is the savior of calculus. It explicitly writes the denominator, dx or dt. This tiny term defines the clock that drives the system. Let's look at the graphs. On the left, if we plot area against radius, the slope is always 2 pi r. It's a fixed geometric law. But on the right, if we plot area against time, the slope is unknown. It depends entirely on how fast the pump is working. How do we bridge the gap between abstract variables? We use the chain rule. Think of it like a gear train. As gear A spins, it drives gear B, which in turn drives gear C. It's a single connected chain reaction. Notice the gear ratios. A drives B twice as fast and B drives C 3 times as fast. These are our local rates of change. To find the total rate, how fast A drives C, we don't add these rates, we multiply them. 2 times 3 gives us a total transmission rate of 6. This is the mechanical soul of the chain rule. Successive rates multiply. So, how do we bridge the gap between the geometry and the physics? We use the chain rule. As we saw with the gears, time drives the radius, and the radius drives the area. It's a connected chain of influence. And the mathematics matches the mechanics. To find the total speed, we don't add the rates, we multiply them. The rate of area with respect to time, dA over dt, is equal to the geometry, dA over dr, multiplied by the physics, dr over dt. This multiplication is the soul of the chain rule. Let's verify our understanding with a classic trap. Find the derivative of natural log of 5x. Student A blindly applies the log rule and gets 1 over 5x. This is incorrect because he ignored the chain. Student B gets 1 over x, and this is correct. Here is the logic. We treat 5x as a single frozen block. The derivative of the outer log function is simply 1 over the block. But we cannot stop there. We must pay the chain rule tax. We multiply by the derivative of the inside block. The derivative of 5x is 5. The 5 on top cancels 5 on the bottom, leaving us with 1 over x. Now, let's formalize this. In calculus, the chain rule often hides inside function notation. You'll see it written as f of g of x. This is a composite function. G is inside f. The formula tells us differentiate the outer function, Evaluate it at the inner, and then multiply by the derivative of the inner. It is strictly a two-step process. You touch the outer layer first, you touch the inner layer second. To make this foolproof, I use the frozen box strategy. When you see a messy composite function, do not panic, just freeze the inside. Step 1. Identify the inner function and draw a physical box around it. Step 2. Differentiate the outer function only. And critically, step 3. Copy the frozen box contents exactly. Do not change them yet. Only after you have handled the outside do you multiply by the derivative of what was inside the box. This protocol protects you from algebra errors. The inside waits its turn. Let's practice this with an abstract problem. We are given a table of values, and the function h equals f of g. We need to find h prime of 2. First, put the numbers aside. Write the structure using the chain rule. H prime of x equals f prime of g of x times g prime of x. Now, substitute 2 for x. We work from the inside out. First, we need g of 2. Looking at the table, g of 2 is 4, so the problem simplifies. We need f prime of 4 times g prime of 2. Back to the table, f prime of 4 is 5, g prime of 2 is 3. We multiply them to get our final answer, 15. Now, for a brain teaser. What is the derivative of a function composed with itself? F of x. Use the frozen box. The outer function is f, so we get f prime of the box. The box contains f of x. Then we multiply by the derivative of the box contents. The derivative of f of x is f prime of x. So the result is a chain of slopes. F prime of f of x multiplied by f prime of x. Here is a harder one. Puzzle 2. Find the derivative of f of x with respect to f of x. This looks like a notation nightmare, but we can wake up from the nightmare using substitution. Let u equal the numerator, f of x, then the denominator is just f of u, which we call v. We are looking for du over dv. Since the derivative of v with respect to itself is 1, applying the chain rule results in du over dv being just the reciprocal of dv over du. Since v is f of u, the derivative dv over du is just f prime of u. So our answer is 1 over f prime of u. Substituting back, the final answer is 1 over f prime of f of x. Just like the movie Inception, the substitution symbol is the kick that allows us to escape the nested levels. Before we tackle more advanced challenges, let's defeat a final boss, trigonometric notation. This is where most students lose points. Compare case A and case B. They use the same atoms, sine, x, and 2, but the structure is totally different. In case A, sine is the outer layer, the 2 is inside, but in case B, the exponent 2 is in the outer layer, the sine is inside. This changes the physics entirely. Case A gives us cosine times 2x. Case B gives us 2 sine times cosine. The position of that little number 2 changes the entire chain reaction. The golden rule is, if you see an exponent on the function name, rewrite it with brackets immediately. It is the only way to remain safe. Well, every rule comes with its exception, and this rule is no exception. See the slide for the caveat. Let's apply the peeling onion strategy to a composite function, sine of x squared plus 1. Most students panic here because they see multiple layers at once. Don't panic, just freeze the inside. Pretend that x squared plus 1 is a solid block of ice. You're not going to touch it yet. First, we differentiate the outer shell only. The derivative of sine is cosine. Notice we haven't touched the inside yet. So, we start writing our derivative. Y prime equals cosine of that frozen block. Now we just copy the frozen inside part down, exactly as it is. It remains unchanged in this step. Finally, the chain rule says we must multiply by the derivative of that inside part. The derivative of x squared plus 1 is 2x, and there is your result. As we saw in the peeling onion animation, complex functions are just like Russian dolls. We have a power function, wrapping a trig function, wrapping a polynomial. We peel the first layer, the power rule, bring down the 3, keep the inside the same, and square it. We peel the second layer, the sine. It becomes cosine. Again, we keep the innermost x squared plus 1 frozen. Finally, we reach the core. The derivative of x squared plus 1 is 2x. The final derivative is the product of all 3 peels. This is the chain rule, generalized to multiple layers. You just keep multiplying until you hit the raw variable x. Now, what happens if we never hit the variable x? What if we hit a y? Let's look at a real-world example. Imagine a rocket launching. Its altitude h increases over time according to this quadratic formula. As the rocket climbs, the atmospheric pressure P drops exponentially. Notice that pressure depends on height, and height itself depends on time. 3, 2, 1, launch. Watch how the variables interact. As time ticks forward, height squares and pressure drops rapidly. It's a chain reaction. The question is, how fast is the pressure changing with respect to time? We have pressure in terms of height, but we need the rate in terms of seconds. We apply the chain rule. First, we differentiate the outer pressure function with respect to height. The exponential stays the same. Then the chain continues. We multiply by the derivative of the exponent with respect to height, namely negative 0.1, and finally we multiply by the rate of the height itself, dh over dt. Since the height is 5 times t squared, its derivative is 10 times t. We plug that in, and we have our total rate of change, physics times geometry. We just saw with the rocket how vital it is to track variables. Let's try one last check. Find the derivative of y cubed with respect to x. Student A says 3y squared. He is wrong. Student B says 3y squared times dy over dx. And he is right. But why? Look at the denominator. We want slope with respect to x. That is our target currency. But the variable we hit is y. There is a mismatch. Y is not x. Y depends on x in some unknown way. Because the variables mismatch, we must pay the chain rule tax. We differentiate the y cubed normally to get 3y squared, but then we must attach the conversion factor dy over dx. I call this the penalty. The easy part handles the power rule, but the penalty accounts for the fact that y is moving. If you forget the penalty, you're assuming y is the original independent variable x, which breaks the physics of the problem. This leads us to implicit differentiation. Look at the circle. It is cumbersome to isolate y, so we differentiate blindly across the equation. Every time we hit an x, we are fine, but every time we hit a y, we pay the chain rule tax, dy over dx. Now consider related rates. Here we differentiate with respect to time, t. Look at the equation. Does x match t? No. Does y match t? No. Every single variable is a mismatch. This means every single term pays the tax, dx over dt and dy over dt. Finally, what if we use a middleman? In parametric equations, x doesn't drive y directly. Time drives both. Another example of an indirect approach investigating the slope in case of parametric looking at the inverse function. The slope dy over dx. Let's see y is the ratio of the vertical and horizontal velocities. We don't have y in terms of x, but we have y in terms of then dividing the equation
we apply
through
the
by
chain
dx
rule
over
to write
dt
the
gives
derivative
us
of
dy
y
over
with
dx
respect to
as the
t
ratio
as the
of
product
dy over
of
dt
derivative of
to
y with respect to
dx over
x
dt,
and
which is the
derivative of
ratio
x with
of
respect to
vertical
t.
velocity to the horizontal velocity. We have seen this formula before. Remember when? To summarize, the slope dy over dx is simply the vertical velocity divided by the horizontal velocity. The time variable cancels out, leaving purely geometry. And for the inverse functions, the logic is similar. Since a function and its inverse are reflections, their slopes are reciprocals. To find the slope of the inverse, you just flip the slope of the original. The way this follows from the chain rule is very similar to what we have done with inception derivative. Please refer back to those slides. We end with the horizon. What happens when a quantity, say z, depends on not one but two independent variables, say x and y? We can trace multiple paths of influence. T affects both x and y. The total derivative is simply the sum of all these chain reactions. This is the gateway to multivariable calculus. Thank you.